Welcome to The Explainer. Today, we're doing something a little different. We're not just looking at some off-the-shelf drone, we are breaking down a professional, one-year master roadmap to design a military-grade surveillance UAV totally from scratch, all based on expert engineering guidance.
Okay, let's just dive right in. The mission here is crystal clear, and it's all about pushing the limits of engineering, not aggression. You know, setting a goal that's this specific, this ambitious, that's really the first thing that separates a weekend hobby project from a legit, professional prototype.
And right from the jump, the source material puts up these critical ethical guardrails. This whole journey is about ISR, that stands for Intelligence, Surveillance, and Reconnaissance. It's about building a reliable eye in the sky, not a weapon. The focus is purely on the huge engineering challenges of staying in the air for a long time and getting stable data.
So where do you even start? Well, the quest begins with the absolute non-negotiables. The first 3 months are all about the core physics that literally keep an airplane in the sky. You just can't build a skyscraper without a rock-solid foundation, right? Same idea here.
Now, these aren't just buzzwords you memorize for a test. Really, truly understanding how these forces play off each other is where so many projects fail before they even get off the ground. For instance, you might think, hey, I'll tweak the airfoil shape to get more lift. But that small change could create so much drag that it just kills your flight time. Mastering these trade-offs, that's fundamental.
And this reveals the core philosophy for any surveillance mission. Endurance is king, period. You don't want a fighter jet that zips by in a flash. You want an aircraft that can loiter, just patiently circling over a target for hours. In surveillance, those extra minutes of loiter time can make or break a mission. And this one single trade-off dictates pretty much every other design choice you're going to make.
So how do you bring these ideas to life? I mean, you can't just sketch them out on a napkin. Engineers use powerful, specialized software, and OpenVSP, a tool actually developed by NASA, is a critical one. This is how you model and analyze a design long before you ever cut a single piece of material.
Okay, so once you've mastered the body, it's time to build the drone's brain and its nervous system. This is the part where the machine really, truly comes alive.
This is where you got to put on your electrical engineer hat. It's this complex dance of calculating a super precise power budget, matching the perfect motors to the right propellers for max efficiency, and then integrating this whole suite of sensors, like the IMU and GPS, that tell the UAV where it is, how it's oriented, and how fast it's going. And this concept right here, this is the secret sauce for autonomy. Think of PID control as the drone's internal sense of balance. It's a nonstop feedback loop in the software that's constantly asking, am I level? No? Okay, adjust. How about now? It makes thousands of these tiny little adjustments every single second to stay perfectly stable. It's what turns a wobbly craft into something that can fly itself.
All right, now the roadmap really starts to escalate. With the fundamentals of flight and control totally locked in, the focus shifts to the highly specialized skills you need to pull off a true ISR mission.
And look at that, our old friend the core philosophy of endurance is back. But now it's being applied at a much more advanced level. From here on out, every single decision is ruthlessly optimized for one thing and one thing only: maximizing time in the air.
So this involves stuff like designing those long, thin, super efficient wings, what engineers call a high aspect ratio. It means planning the entire mission from start to finish, understanding the limits of your communication links, and then engineering the payload, the cameras and gimbals, to be perfectly stable and effective.
And this slide right here illustrates the constant, unavoidable battle that engineers face. Every single gram you add for a better camera or a fancier sensor directly cuts into your flight time. There is just no free lunch in aerospace engineering.
And now we're in the home stretch, the final phase. This is where all the theory, all the design, all the specialized skills, it all comes together in one single professional-grade project that you can actually showcase.
So what are we talking about at the end of the day? These are the real-world specs for a final prototype. I mean, a sophisticated aircraft with a wingspan around 2 meters, capable of flying completely on its own for up to an hour and a half, all while sending back a live data feed. This is a serious piece of engineering, and it's all legal and safe to operate.
But here's the thing. What makes this defense grade isn't just the drone itself. It's all this documentation that proves the engineering rigor behind it. The CAD models, the simulations, the failure analysis, this is what shows you didn't just build a cool toy, you engineered an entire system.
Finally, woven through all these phases, there's something you can't really touch, but it's just as important. It's a specific way of thinking. This is the mindset that separates hobby projects from true, defense-grade engineering.
It starts with redundancy. You never ever want a single point of failure. So you build in backups. 2 GPS units instead of 1, multiple power lines, so that if one little component fails, the whole mission isn't over.
Then you have fail-safe design. This is all about planning for what happens when things go wrong. If the system does fail, you want it to fail into a safe state. The classic example is programming the UAV to automatically return to its launch point if it loses the communication signal.
And finally, there's graceful degradation. This is the idea that the UAV shouldn't just fall out of the sky. It should lose its capabilities bit by bit, not all at once. So maybe a secondary sensor fails, but the primary one keeps the aircraft flying safely, allowing it to finish a reduced but still useful mission.
So at the end of it all, this is how you frame the project. And listen to those words: optimized, persistent, reliability. See? It's not about what's cool or how fast it is. It's about capability and dependability. That's the language that professional organizations and defense agencies really value.
So I think the crucial point of this entire roadmap is that the process, that's the real product. The drone is kind of like the final exam, but the engineer you become along the way, that's the ultimate outcome. It really leaves us with a final thought, doesn't it? What complex challenge in your own world deserves this kind of methodical, disciplined mastery?